Okay, so I'm going to show you today a spectral decomposition of the ground state of helium. Now, if I ask you what a spectral decomposition of a hydrogen atom is, you'd just list me the eigenfunctions and the eigenenergies. We can't do that with helium because it's too complicated. So we're going to do the next best thing, which is to project the helium wave function onto a hydrogenic basis. So I'm just going to try and motivate why we would do that, briefly show you how it's done, the results, and then talk about some implications for research. Okay, so we can start with the question, what is the ground state wave function for helium? And again, we don't have an answer in an analytical form because the Hamiltonian has this nasty electron-electron interaction term. If that term wasn't there, then the solutions to the Schrodinger equation would just, the Schrodinger equation would have separable solutions, which are just products of hydrogenic ground states. So many of you have, probably all of you have seen hydrogenic states. Most of you have probably derived them. They're just those Laguerre polynomial spherical harmonics. And some of you have probably taken a step a bit further even and used first order perturbation theory with this term as the perturbation Hamiltonian and your unperturbed wave functions as hydrogenic ground states. And you would have calculated the ground state energy to be this value, which differs from the experimental value by 4 electron volts. 4 electron volts is a significant difference. So what this says is that hydrogenic ground states alone are not enough to account for the helium ground state. So instead of going to more advanced approximation methods, we're going to stick with this kind of paradigm of thinking of helium in terms of hydrogenic states, because this is the kind of thinking that underlies a lot of our intuition about chemistry and solid state. So instead, we're going to ask exactly what hydrogenic states do we need to compose the full helium ground state. In other words, we're going to decompose the helium wave function into a complete basis set, which consists of hydrogenic bound states and continuum states as well. And if we take the inner product on both sides with the nth hydrogenic state, we'll get these integrals, which are the projections that I'm talking about. The square of these coefficients gives us the contribution of the nth state to the full helium ground state. All we need to do is put in a trial wave function for psi exact, and we choose that wave function based on how well it approximates the ground state. So 1928, a man named Hillerus did this for us. He came up with a very nice trial wave function based on some variational parameters that you can set, and it reproduces the ground state to within 0.05%. So we're safe in using this as a valid approximation to that psi exact. So we stick it in the integral, and we compute these projections. Now, I could try to do this numerically on a case-by-case basis, but I don't want to do that because I'm interested in the convergent behavior of large quantum numbers. So I actually wanted a general form for this integral for any quantum numbers, and this integrand is hideous. You can't just stick it into an algebraic solver and ask it to solve it. It just won't be able to. So I spent about 6 weeks deriving an analytical expression for this integral, and I won't show it to you because I can't fit it on one slide. But in any case, I can program that into something like Mathematica and just feed it a list of quantum numbers, and I can compute these bound state contributions, these CNs. And if I take the square of those CNs, that gives the weight of the nth state in composing the helium ground state. And if I add up all of those squares of CNs, then I get this curve. So I start with the ground state, the 1001000 state, or the 1s1s state, as I'll refer to it from now on. And you can see that that doesn't even make up 93% of the actual helium ground state. And I can keep adding more and more states, and you see it quickly converges to a value distinctly less than 1. That means that the bound states alone are not enough to account for the full helium ground state. So we have to go and compute those coefficients for the continuum states, and that's a lot more difficult. So I spent more time doing that. And we make one approximation, which is that we're only going to consider as our basis, the states in which one of the electrons is in the ground state and the other one is in a continuum state. And we're going to see how much those states contribute to the end result. So we do the same thing. We compute that projection, that integral, only this time it's a 12-dimensional integral, so it's a lot more hideous, but with some miracles of hypergeometric functions, it can all be done. And when we integrate over all momenta, we get that extra 1.17% that we're looking for. So it's true that the continuum states do indeed contribute. Now this might seem a little strange because continuum states are plane waves. They describe ionized electrons. And we know that helium's inert, so are we saying that 1.17% of the helium ground state is really an ionization state? Well, that's not true because, of course, we can construct an arbitrarily localized wave function just by taking linear combinations of plane waves. So this is great. We have an explicit decomposition of the helium ground state into all the hydrogenic bound states, as well as the continuum states, that extra 1.17%. And the important thing, probably the most important thing to grab from this, is that that considering only the 1s, 1s state, product of hydrogenic ground states, makes up less than 92.5% of the full helium ground state. The rest is excited in continuum states. So what does that mean for research? Well, it has two implications I want to talk about. The first is what I'll call electron-hole asymmetry. So let's consider a chain, a one-dimensional chain of hydrogen atoms. These white circles represent just a regular hydrogen atom has one electron, and these green circles are sites where a second electron has come and joined the atom. And we can think, we're used to thinking about electrons hopping between sites in the exact same way as we think of a positively charged hole that it leaves behind hopping between sites. So if electrons are moving from right to left here, the hole can be considered to be moving left to right. But let's stop and think about exactly what we're doing here. We're considering the one electron state to be the 1s state. That's completely valid. The one electron state is just a hydrogen atom. We can consider it in its ground state to be the 1s state. But this two electron configuration we're assuming is the 1s, 1s state. We just saw, though, that this state makes up less than 93% of the total helium ground state. So this is not true. In reality, the two electrons occupy a linear combination of the 1s, 1s state, as well as all the excited hydrogenic states and even continuum states. So what that means is each time an electron pops over a site, the electron that it leaves behind has to relax back down to the ground state. So in other words, if an electron takes one time step to move over one site, the hole takes this many time steps because the electron that it left behind is in some combination of not just the 1s state, but also the excited states, and therefore has to relax back down to the actual ground state. So what this means is that holes move more slowly than electrons. We can't really think of motion of electrons and motion of holes as being the same, as being equivalent. So the second implication I wanted to mention was a correction to the Hubbard model. So the Hubbard model is one of the go-to Hamiltonians for solid-state physics. It's very simple. It consists of a kinetic term, which is the hopping term that represents the motion of the electron as it hops between sites. And it has a potential term, which is simply the repulsion of two electrons on the same site. But again, this is the repulsion due to two electrons in that product of hydrogenic ground states, that 1s, 1s state. And once again, we know that a real two electron configuration we saw is in fact not in the 1s, 1s state. In fact, there's a significant contribution to that configuration where one of the electrons is excited, and if two electrons are in two different spatial states, this repulsion is going to be significantly reduced. So it's hard to get an idea of exactly how much that term needs to change, how much we need to adjust it, and that's definitely where future work would go with this. But to get a kind of vague idea of how big of a problem this is, let's remember the first thing I showed you at this presentation, which was that first order perturbation calculation. Keeping that in mind, we can extend this, this thought experiment to atoms which have not just a chain of one-dimensional hydrogen atoms, but also any atom which has a single electron in its valence orbital. So what about copper? We always just ignore the inert core, and so this system, for the purposes of many models, is just the same as that one-dimensional chain of hydrogen atoms. What if we're modeling copper in a YBCO superconductor, and we want to know about electrons moving amongst that copper lattice? Well, the first order perturbation calculation I showed you said that if we only consider an electron that comes to join this atom to be in the 1s state, then our energy calculation would have a discrepancy from the actual value of 4 electron volts. 4 electron volts corresponds to 46,000 Kelvin. If we're trying to model superconductors, even high temperature superconductors that exist at tens of Kelvin, then this is a serious problem to the models. So in conclusion, the whole notion of considering a 2-electron system to be equivalent to a product of hydrogenic ground states is seriously flawed. And I'd just like to thank the following people for advice in some of the derivations. Any questions?
Can you tell us more about the test function that you use for the perturbation model? For example, what it looks like and why you used it?
Okay. The test function was the Hiller's function. So how you can motivate it simply by saying, well, the only variables it should depend on are these 3 interaction distances. And those are the only variables that appear in here. And the other restriction you'd want is that to first order, this expression should reduce to the product of hydrogenic ground states, which it does, if you just consider this term, the one term. Really, Hiller's came up with an arbitrarily long expansion. So this is only actually a 3-term expansion. You can include more and more terms, all depending on R1, R2, and this separation distance. I think some people have even done it to 117 terms. Each term has a variational parameter, and you just set that parameter using the variational principle. You minimize the ground state energy with respect to those parameters and then set them that way. And the point is just that if we do calculate the ground state energy using this function, it's within 0.05% of the experimental value, so it's a very accurate trial weight function.
So when you say within the 0.05%, that's just with those terms you have there.
Yes, exactly. You can get arbitrary precision.
Maybe I missed it, but you don't seem to consider the change of charge in liquids. Is that
right? So when I say, I should probably mention that when I say a hydrogenic state that can have any nuclear charge, you put that value in explicitly.